So we're talking about polyatomic ions here. And as I mentioned before, this is a list of them. And really the best way to sort of learn them is sort of through memorization. And as I mentioned, they're really all related. There's a number of them that are related to each other. And the main difference between different polyatomic ions is really only the number of oxygens that are present. The charges are all the same for everybody that's related. It's just those number of oxygens. And again, the one with the most oxygens, as I mentioned, in a group of two, like I wrote earlier, the nitrate, ATE, and the nitrite, is, again, this entire thing has a -1 charge. The nitrogen 2 oxygens has a -1 charge. And again, the one with the most oxygens ends in 8. So as I mentioned, sometimes people do like to just remember one of them and know, if you need the 8, add an oxygen, or if you remember the 8s, you need an I, just lower the number of oxygens. Other things that we talked about was, again, the relationship between a group of 4, and this is the most common group of 4 that are related to each other that we were talking about there at the very end. And they all have a -1 charge, and really the only difference between all of them is how many oxygens each one has. So in a group of 4, like I said, you could kind of break it up by pairs here. And the 2 on the right basically have the least number of oxygens, so they should end in ITE. And that would make this guy chlorite. And that would also make this guy chlorite. Once again, you can't really have the same name for 2 different things. So in a group of 4, the one that has the least number of oxygens in that group of 4 will also begin with hypo. So that is known as hypochlorite. Chlorite. And we could do the same thing on the other side here where we have the most oxygens. Each of those should end in 8. So this would be chlorate, and this guy would also be chlorate. But once again, we can't have 2 with the same name. So the guy in the group of 4 that has the most oxygens will start with per. You could actually switch out chlorine for any of the halogens. You could put bromine in there. So if you had something like, instead of ClO3 minus, BrO3 minus, that would not be chlorate, but that would be bromate. So it works the same way. You can just swap out any of those guys there in group 7 and you'll have the same thing. The other common thing that happens is you put an H plus on top of something. So CO3 2 minus is carbonate. And if we put an H plus in front of it, it becomes HCO3 minus. It's an H that goes in front, +1 and -2 leaves us a -1 overall charge. And basically the only thing we did there is put a hydrogen in front of carbonate, and that is the name, hydrogen carbonate. Now, hydrogen carbonate is sometimes replaced by bi. Sometimes people will call it bicarbonate instead of hydrogen carbonate. They also do it for sulfate. They'll call it bisulfate instead of hydrogen sulfate. So it's the same thing, just an old sort of way of naming something that people still really use a lot. Now, not all polyatomic ions actually end in 8 or ite. There are some like OH minus that end in IDE, that's hydroxide. There's also cyanide, which ends in IDE. So there are a few polyatomic ions that actually will end in IDE, but a vast majority of them are negative, and a vast majority of them will end in 8 or ite. And like I mentioned before, what usually will happen is you will have these guys basically hooked up with a metal. And really what you fall back on is it's an ionic compound, so positive, negative. And naming it that way. So why don't we try some here? Let's do CaOH2. Let's do CuCO3. let's do let's do E2SO4. All right, so why don't you give that a try? Those guys give the proper name. And then let me give you a couple of names and you try a formula here. We'll leave the table up there so you can kind of look at it. Let's do chromium 3 nitrate. Do barium, hydrogen, carbonate. All right, the two on the right there, let's do formulas and then names for the guys on the left there. Okay, let's take a look. So once again, we want to identify what we got going on. We got calcium, which is a metal. We have OH, which hopefully you'll recognize is OH minus, which is a polyatomic ion. So really, this is sort of a type 1 compound because we do have a type 1 metal. So remember, if you got the metal involved, it's the most important thing. Type 1 means it has a fixed charge, right? Because that's calcium with group number 2, which means we don't need any Roman numerals or anything like that. We're just going to use the whole name of the metal, which in this case would be calcium. And again, the polyatomic ion here is just like a normal type 1 sort of compound. We just actually use the name of it, and that would be hydroxide. Should be 2 words, kind of squished them together there, but should be calcium hydroxide there. Once again, the 2 here has no effect on the name. We use the 2 there to say we have 2 hydroxides because calcium is +2. Calcium is +2, and each of the hydroxides are -1. So that gives us -2 and +2. So everything balances out to 0. Because ultimately here, these are really just positive, negative guys that need to equal 0. And again, but it has no effect on the name. So calcium hydroxide would be the name there. On this one, that is copper, which is a metal. That is CO3, which is CO3 2-, which is right here. And that is carbonate. So once again, we look at the metal. Do I need a Roman numeral here? The copper is a transition metal, which means it is a type 2 compound, and you do need to figure out the charge on it. So in this case, I have a copper. I'm not sure what the charge is. Knowing that this is carbonate, the carbonate is CO3 2-. That means that entire thing has a -2 charge, which means the copper here would need what type of charge to balance it out? +2, just like normal, right? To balance out the positive, negative. That means that the name here should be copper Roman numeral 2 because of the charge on the metal. And once again, here we will use the entire name of the polyatomic ion, which would be carbonate. So this would be copper Roman numeral 2 carbonate. Question on that name? All right, coming here to iron, which is a metal. SO4 is sulfate, which is a polyatomic ion. Do I need a Roman numeral for iron? The answer is yes, I do. So you need a Roman numeral for any metal that's a transition metal, or just to the right of it, which is like lead and tin. The ones that do not need Roman numerals are type 1 guys, which is group 1, group 2, group 3, zinc, cadmium, and silver. Those guys have fixed charges, so you don't need any Roman numerals. So once again, here we do need to figure out the charge. So I have not 1, but I have 2 irons in this case. And I actually have 3 sulfates. So that is SO4 2-, SO4 2-. One more, we'll go on top. SO4 2-. That is a -2, -2, and -2. That is a -6 in this case. Each iron to balance it out needs to be what charge? It does need to be +3 in this case. So each of these irons would be +3. And we would need a Roman numeral. So this guy's name here would be iron Roman numeral 3 for the charge. And again, even though there are 3 of these sulfates, it has no effect on the name. It would just be sulfate at the end. So iron Roman numeral 3 sulfate. You can, again, as we talked about, I think last time, it works, most of the time, but not all the time. In this case, it would work. So you'd be okay in this case. But remember, just don't blindly do that because it doesn't always work. But not, it will work. But again, there are definitely places where it won't. But you can do the switch over if you want. Other questions? Now, if we want the formula here, we just want to kind of put everybody together properly. So since these are really ions, the same goal of 0 is what we're looking for. So chromium Roman numeral 3 means that the chromium has what type of charge? Has a +3 charge. That is what the Roman numeral means. Nitrate from our table here is NO3 minus. Do I need more chromium or more nitrate to get to 0? I need more of the nitrate to get to 0. I need 3 of them, right? Because if I put another couple in there, that is -1, -2, -3, which balances out the +3 that I got going on there. That means that the formula here would be Cr. Because there is more than one of these polyatomic ions, I need to put a parentheses. NO3, and on the outside of the parentheses on the bottom, how many I got going on, which would be the 3. Yeah. The reason you need the parentheses is if you wrote this CrNO3 3, what does that mean? You have 33 oxygens, which is not really the case here. So you do need to put the parentheses around the polyatomic ions so that it says you basically have 3 of those units and stuff. Question on that one there? So barium hydrogen carbonate. Barium is group 2, which means it has a +2 charge. Hydrogen carbonate's on our list here, I think, right there. So it is this guy, HCO3 minus. Again, that hydrogen carbonate has an overall charge of -1. So in this case, we actually need more of the bicarbonate to balance it out, right? We would need a grand total of 2 of them. That gives us a -. Now we could just write what we got going on there. Here in the middle. Ba, we would need parentheses, HCO3 and a 2 on the bottom. Yeah. Once again, we need the parentheses because we have more than one of those polyatomic ions. Question on polyatomic ions. Again, for the most part, it's pretty much going to be hooked up with a metal. And you really could just fall back to type 1 or type 2 sort of rules. And it basically boils down to the metal's still the most important and whether or not you need a Roman numeral or not. And the nice thing about polyatomic ions is, frankly, it doesn't matter how many you have of them. You just use the name of it. So it doesn't matter if you got 30 of them or anything like that. You just use the name. Now, we talked about prefixes, and you should never use prefixes with like type 1 and type 2. This would be the only place where a prefix could come into there. And it's because the actual polyatomic ion, for example, has a prefix. So for example, that guy's name is dihydrogen. It just happens to be a prefix in the name. That would be the only case where if you had a Roman numeral and a prefix, it's okay because it's actually the name of the polyatomic ion. But you should never put your own prefix in when you're doing any of these type of namings as well. Any questions on polyatomic ion naming? Naming in general. Yeah. I think we talked about it, but just to make sure I got everybody here. If we had something like HCl, that is called what? This is hydrogen chloride, right? Now, this is both nonmetals, but they're very much treated like sort of an ionic compound. So this is really thought of a lot of times as H+ and Cl- coming together. So we really do kind of name this more like a type 1 compound, even though it's really two nonmetals together and hydrogens involved. So if you have something like H2S, this would be hydrogen sulfide. So hydrogen is always the first name there, and IDE on the second guy. And hydrogen, again, sort of a little bit different. It's kind of treated almost like a metal, but even though it's really not. And that's why we have two of the hydrogens in this particular case. Any questions on that there? Yeah. Yes. Yes. And again, type 1 and type 2 are ionic compounds. So those are either Roman numerals or no Roman numerals, metals and nonmetals. Type 3 is where we use our prefixes for the two nonmetals. And then really our polyatomic ions have special names for everybody. So you do need to know the names and obviously the charges so you can put everybody together correctly. But those two, as I mentioned, kind of fall back into type 1 and type 2 naming in most cases. Yeah. Other questions on that? Okay, so we're going to talk a little bit about then chapter 7, which is equations and balancing equations, which I think will be helpful this week here. Kind of chapter 7 notes here, and we're going to talk a little bit about the balancing equation parts and all that. So all chemical changes can be represented by a chemical equation, and a chemical change is really a chemical reaction that takes place. What we have up on top is a balanced chemical equation. And whenever you use equations in chemistry, they should always be balanced, which basically means we have the same number of elements on both sides of the arrow. And if we look over here, there's 2 times 2, so there's 4 hydrogens on the left. There's 2 times 2 is 4 hydrogens on the right. There are 2 oxygens on the left. And if we multiply 2 times 1 here, would give us 2 oxygens on the right-hand side. The idea of that is the law of conservation of mass. In a chemical reaction, we never change the elements. So the only thing that happens in a chemical reaction is all the bonds break and they reassemble on the other side and make new compounds and stuff. But we start with 4 carbons, we'll end with 4 carbons. They may just be in different places when the reaction is all said and done. Now, the arrow to the left-hand side of the arrow, those are what are referred to as reactants. Reactants are your starting material. So these guys here would be the reactants. And that's always found on the left-hand side of the arrow. And on the right-hand side of the arrow is the products. So the products are the stuff that is basically made as a result of the chemical reaction. Some other things that we sometimes will see on top of the arrow, we will sometimes see things written like PT or H+. Sometimes written up on top are what are referred to as catalysts. And catalysts are not reactants. They're not products. They do not get used up. In the reaction. They are typically there just to speed up the reaction. So a lot of times catalysts are added to reactions to make the reaction occur a lot faster. And a lot of times in terms of equations, they're a lot of times written up on top of the arrow, and those are usually catalysts. Other things you'll sometimes see up on top of the arrow is you'll sometimes see like a little delta symbol, and that usually means heat was sort of applied. You may even see up on top of the arrow like water written, which usually means something was dissolved in water. So that's another sort of thing that's sometimes put up on top of the arrow. In addition to the chemical formulas, we sometimes will see the states of everybody. So you'll sometimes see like an S next to something, which means it's a solid. You'll see an L next to a formula, which means it's a liquid. You'll see a G next to a formula, which means it's a gas. You'll see an AQ next to a formula, which means it's aqueous. So these are some of the states that we very commonly will see in a reaction. There is a difference between liquid and aqueous. Liquid is a pure liquid, something by itself like water. So if you had just water by itself, it would be a liquid. Aqueous is usually a solution, which means you take 2 things, you mix them together, and you make a solution. So for example, water would be a pure liquid. If you took sodium chloride, that's a solid, and you dissolve those guys together, you get basically a sodium chloride solution that gets an aqueous symbol. Salt solution basically is water, and salt dissolved in it is an aqueous solution. But water just by itself is a pure liquid. So there's a difference between those two states. Any questions on that there? Yeah. Yeah, it's a delta symbol. Sometimes in equations up on top of the arrow, it's used to indicate that heat is maybe being applied or something like that. No, you should do like something like that. That's another delta symbol. Yeah. That's a delta symbol. That's kind of like the delta symbol that we use for like positive, partially negative. So this little symbol here is a delta symbol. Usually, I would say in equations, usually you'll see the triangle for heat. You don't usually see that. Usually this delta symbol you'll see for electronegativity and partially positive and partially negative charges is sort of the delta symbol that you see for that. But usually for if you're just talking about an equation or a reaction and you want to imply that there's heat or something being off, usually most people just use the triangle for that. But they're technically both delta symbols. So other questions? All right, so reactants goes to products in a reaction. Now, it's really important to always have a balanced equation. So let's talk about some strategies you could use, although most people just kind of use a trial and error approach, which usually works most of the time. But basically, first off, if you happen to be given everything in words, for example, you want to make sure that you start out with the correct formula. So sometimes you may be given everything just in words. So like naming and nomenclature, you want to start out with the correct formula first, and then you want to balance it. Also, if you have like the reactants and you need to predict what's on the product side, you want to get the right formulas on the product side and then balance the equation. Sometimes people try to do both of those things together. What ends up happening is you end up with the wrong formulas and you'll sit there all night trying to balance something that will never ever balance because you don't have the right formulas. So keep that in your head that you should always get the right formulas and then balance. Don't try to do both of those things at once because you will screw up most likely. Once you have your right formulas down, that's the unbalanced equation. You can begin balancing, which really, personally, I go with whatever seems kind of easiest to fix. It's usually a good idea. I personally like to make a table of how many we got on the reactant side of something and how many we got on the product side. The table oftentimes will help you sort of visualize maybe where to start balancing it. The most important thing is we balance equations by only changing the coefficient. So only the number that comes in front of the formula gets changed. So if we had something like water, we only change the number here. We never change this number because what happens if I change that number? It becomes something else. It's no longer water. So we never change that number. We never put like a number in between elements or anything like that. Only the coefficient that comes in front is the only thing that you could change. You basically keep doing that until you got the same number of elements on each side. When you have a correctly balanced equation, there's two things that you need to have. They need to all be whole numbers, the coefficients. And they need to be the simplest set of whole numbers. So what I mean by that is, for example, let's just say we balance this equation. 2a plus 4b gives me 6c. And we'll just say it's balanced. And these were the coefficients that we used. And although we might have hit everybody balanced, in this case, I could do what with all those coefficients? I could divide by 2. And you should. And it sometimes happens because sometimes people see bigger numbers and they get it balanced. But if you could reduce down the coefficients, you should always do that. So if we ended up with something like this, we would want to reduce it down by dividing by 2. And we would end up with this equation, which would be the properly balanced equation. So again, sometimes people can see the larger numbers and it's absolutely balanced on both sides. But if you look at all your coefficients and you can reduce them all down and still end up with whole numbers, you should definitely do that to get the properly balanced equation. Any questions on that there? All right, so let's do one here together and make sure. All right, so if we have this equation and we want to balance it, here is my approach. I would make a little table and I would have the reactant side, I would have the product side, and I would just list the elements. So I got nitrogen going on, I got oxygen, I got hydrogen, basically. So all I'm going to do is just take an accounting of where I'm starting. On the left-hand side, there's one nitrogen, which is right here. Right-hand side, there are two nitrogens. Left-hand side, there's one oxygen. Right-hand side, there is one oxygen. Left-hand side, there is two hydrogens. Right-hand side, there is two hydrogens. Any questions on where I got those numbers from? Again, just the numbers of each of those guys. Now at this point, I have a nice table which, could kind of focus my energy. I could clearly see from my table the hydrogens look good. The oxygens look good, so clearly the good place to start would be, in this case, with the nitrogens, right? So I have one nitrogen on the left, I have two on the right. The goal here is to get to the same number. We can only put a coefficient, so I'm going to put a 2 in front of the nitrogen on the left. When I do that, I now have two nitrogens. The 2 goes for the nitrogen and the guy behind it, so that's basically 2 times 1, because there's one oxygen there. And that would be 2. And then I still have 2 hydrogens. Any questions on that there? Much like what happens when you go to balance the equation, you fix something and you screw up something else. So that's okay. We got a table. We fixed the nitrogen. We can now see we kind of messed up the oxygen, right? Now I got 2 oxygens on the left, but I only have 1 on the right. Not a big deal. I could fix that by once again putting a 2 in front of the oxygen on the right. Now, in terms of the right-hand side, I still have 2 nitrogens. My oxygen is now 2 times 1. And hydrogens, I am now up to 4. 2 times 2, yes? So 2 times 2 is 4. So we're getting closer. We've now balanced the nitrogens. We balanced the oxygens. The last one now is to balance the hydrogen. I could go back to the left-hand side and put another 2 in this case. Popular number here. And if I do that, I now have still 2 nitrogens here. I have 2 oxygens here. And 2 times 2 is 4. I am now balanced on both sides. The only thing I changed is the coefficients. And it looks a little sloppy, so I'll rewrite it here. 2NO plus 2H2 gives me N2 plus 2H2O. And this would represent the balanced equation. Question on that? I would say for most people, that's sort of how they balance it. Put a number, change something, go to the other side, put a number. Eventually what will happen is if you do it right, everything should sort of fall into place. At some point, everything should end up being balanced. If you find yourself there forever and it doesn't seem to want to balance, probably one of 2 things is wrong. Probably you either have the wrong formula somewhere or you're doing some bad math when you're multiplying. The coefficient always goes for all the elements in the formula behind it, and you basically multiply the coefficient by the subscript, the small number on the bottom. Remember, if there is no number, it's assumed to be 1, so that's how come it's 2 times 1 and so forth. Any questions on that one? All right, why don't you try one here then, balance this equation here, see what you come up with. Okay, let's take a look. We got reactant side, product side. So we got some carbon, we got some hydrogen, we got some oxygen going on. Left-hand side, in terms of carbon, there are 3 of them. Right-hand side, there's 1. Hydrogen on the left, there's 8. Hydrogen on the right, there are 2. Oxygen on the left, there are 2. And oxygen on the right, there are how many? There are 3. There's 2 here, plus 1 more over here. Gives us 3, right? So we don't want to miss that one. In this case, we're not much to go with that's balanced, so might as well try something that's not too hard to do. For me, I think the carbon wouldn't be too hard to kind of fix. So we could fix the carbon on the right-hand side by putting a 3 in front of it. When we put the 3 in front of the carbon, it goes for the carbon, which is 3. We also still have 2 hydrogens. Now, oxygens, we were up to how many at this point? We have 3 times 2, which is 6, plus 1 more over here is 7 at this point. Yeah, so that is where the 7 comes from. Now I fix the carbon. Probably the next easiest thing to fix would be the hydrogen, since oxygen's and a couple of things going on there, right? So if I want to fix the hydrogen, I need to put a 4 there in front of it. And if I put a 4 in front of it, I again have 3 carbons. 4 times 2 is 8 hydrogens. Oxygen, I am up to how many at this point? I still have 3 times 2, which is 6. Now I have 4 times 1, which is 4. So that's a grand total of 6 and 4 is 10 oxygens. Yeah. Any questions on that? Yeah. Which is not too bad. I could fix the oxygens by now going to the left-hand side and putting a 5 in front of it, right? If I do that, that is 3 carbons, 8 hydrogens. 5 times 2 is 10 oxygens, giving us a balanced equation here of this. Any questions on any of those steps there? So it's best to take it one at a time. It's best to go after things that are maybe just in one formula on each side. You know, you could kind of tackle those and kind of save something that's in multiple places, maybe till the end. Any questions on that there? All right, let's try another one here. Let's try this one. All right, so balance this equation, see what you come up with. Okay, let's take a look here. So we got boron, oxygen, and hydrogen, I think. So on the left-hand side, we have 2 borons. Right-hand side, we have 1. Left-hand side, we have 4 oxygens, 3 there and 1 there is 4. Right-hand side for oxygen, we do need to multiply the 3 in, so that would give us 3 oxygens. Hydrogens on the left would be 2. Same thing for the hydrogen on the right. We need to multiply the 3 into there as well, and that would give us 3. So not much balance here, not much to work with on the right-hand side, so might as well start there. I think the boron would be the easiest to balance, so we would put a 2 in front of it. When I do so, that gives me 2 borons on the right. Left-hand side, we need to multiply the 3 in, which gives us 3. We also need to multiply it out to the coefficient, and 3 times 2 is 6 for the oxygen, and you will end up with the same for the hydrogen, 3 times 1, and then 3 times 2 on the outside. Any questions on that there? Clearly, at this point, we need to fix the oxygen and the hydrogen, and we don't want to touch anything on the right-hand side because they're all together, and we already put a number there. So since hydrogen is by itself on the left-hand side and oxygen's and a couple of other things, I'm going to just start with the hydrogen. It seems probably the easiest. To get my hydrogen on the left to 6, I need 3 of them. That would give me 2 borons. Oxygen, I have 3 here and 3 more there is 6. And hydrogen 3 times 2 is 6 as well. Actually fixed everybody by just putting the 3 there. We're done at that point. We are balanced. Happens a lot of times. Things fall into place. Things are good. Yay, chemistry. Yes. Any questions on that one there? All right, so since we're kind of out of time, we will lay it up there. At least we got into some balancing. Hopefully that'll be helpful for you.